All right, looks like people are jumping on.
Django, do you want to introduce Songyan, or since this is his first introduction into specs? You're muted.
Yes, I do. So, well, actually, we made a slight change, and so Joe used to be actually our representative for spec, and considering actually that the new emerging area of replacement of ITO with the conducting polymer, and which Songyan has been working on the electrochemical stability of this polymer in electrolyte. So we thought that would be actually a good occasion to make the switch. So here, and Songyan will be presenting actually his findings in the stability of n-PBDF in the electrolyte environment. That's all. That's the background.
All right. Do you want to share your screen, Songyan?
Oh, so am I the only presenter today? Sorry,
Yes.
sorry. Yeah, this is my first time like attending this meeting, so I got no idea. Okay. Yes. Can you see the slide?
Yep.
Okay, yeah. Hi everyone in the meeting. So I'm very happy to present today. Yeah, and also to see some familiar face because I worked with Aaron before. And it's also happy to see Spencer and Dr. Armstrong here. Like we haven't been met for a while. So my research here is actually, you can see it from the title, understanding mixed conduction mechanism in n-PBDF material and the role of ion and the solvent on the transport. So, so basically I'm working on the electrochemistry of this material. So in the meantime, because of all the characterization experiment I have done, so also able to see like this material actually has good stability and durability, at least under electrochemistry. So first I should start with the new material, n-PBDF. I don't know if how familiar you with this material. So organic mixed conductor is a very fancy material. So it has a fascinating application in different applications such as solar cell, flexible, stretchable electronics, and bioelectronics. So one of the most known material is P.PS. I think everyone knows about that. It's very conductive. There's some problem like of this material, like the manufacturing or to make it consistent. So recently in our group, we reported a new N-type material, which called n-PBDF. It has a state-of-the-art conductivity and performance of the than the previous reported N-type material. It's a like saturation-free planar backbone, planar polymer backbone material. And the benefit of this is that it has a very low LUMO level, so it will be stable under ambient condition like water or oxygen. So it will be basically conductive just in the air. So I'm not going to introduce the synthetic work because I'm not the synthetic chemistry. So it's a very fancy material, and it has like the highest reported conductivity even than P.PS. You can see from the middle figure of the pictures, we can see it has a very high conductivity. It has like a relative high transmittance over the our normal and near IR wavelengths.
Disconnected.
Pardon? Can I continue?
I think it was somebody who was just logging in. Here, okay, keep going.
Okay, sorry. So it has very good sheet resistance, and we can say from this figure, we can say that compared to other material, even though ITO, it has a comparable performance. We also have used this one as the conducting polymer to replace of ITO to build an electrochromic device. So we have got n-PBDF as a conductor layer. We have a chromic polymer, and we try to use it in electrolyte, and it shows that very good performance because it's either conductive, both conductive and transparent. So in terms of the stability, okay, the ink has a very good stability and a different temperature. And when we dip it into water, it still keeps the good performance over hours. And we did like a film weathering test over like 2 weeks. It still shows like very high conductivity. And also we got like a whole heating test, and it's pretty resistant to like almost variety of chemical solvents. And we also did a mechanical test for bending, and it's quite flexible. So overall, it seems to be the best mixed conductor material ever. However, like we can not only test it into like a normal test. For different research, we want to have different application. Most of the cases, we want to build electrochemical devices. So we would like also to understand its stability under electrochemistry. I think if my understanding is correct, like in this project, we would like to build like a photo electrochemical cell with n-200, I suppose. And also we need to have like ITO as a conductor for the heterojunction. As I said, like n-PBDF is transparent as conductor, so it has a possibility to replace ITO as a conductor. So what's the problem with ITO or the transparent oxide conductor is like the mineral, it's kind of supply is limited. It's also like some kind of like toxic in bioelectronics. And for example, indium like is mostly used one. So, but it's reserved, like it's mainly controlled by a few countries like China. So, and also ITO is quite a bridge, so it cannot actually bend or make a flexible polymer substrate. And also it cannot be solution process, so it can may cause problem in manufacturing. So also in terms of our specific goal, I think like allow me to just take a few pictures from previous slide. I think like when you will use ITO as a conductor, as a problem is reproducibility, and because of like it has like a relatively higher work function, and also because it has hydrophobic like surfaces, it can catalyze other cell reaction. So for example, if in water, so like the water will accumulate like between the polymer and the glass and cause some delamination of the film. I mean, there's some like strategy I have seen, like people are trying to use like HI or SAM treatment or use cross-linker, so it can enhance the adhesion of the polymer to the substrate. However, since we got this new conductor, why couldn't we just replace this ITO into and use n-PBDF? I mean, then we will have like a polymer and polymer interface, so many problems ITO has just can be eliminated. So my research is not for device fabrication, so it's for electrochemistry. But I think it's better to start just from electrochemistry to see how it's performed like in electrolyte. Because I mean, finally we will to put this device into electrolyte. So here's like a brief introduction of like a mixed conduction mechanism. So basically we have separate process. Like we got ionic charge injection and ejection transporter from electrode to polymer. We got ionic and electronic coupling. I mean that electronic charge carrier stabilized by ion. We also have like electronic charge transport within this polymer, and then we have the electronic charge injection and ejection between the polymer and electrode. So to understand this kind of, there's many different ways we can tune the structure. We can have different processing strategy. We also a simple way just we change the electrolyte to see what happens. All this strategy will just alter the microstructure of polymer, and also alter the ionic transport, electronic transport, and ionic electronic coupling. And then we will have say a different performance of the device. So what I done here is not difficult. I just change the electrolyte. So basically, like, we know it's an N-type polymer. So first, idea commitment. Okay, we change the chi-die. So here we have lithium, sodium, and TBA. And also some literature has reported that the ion can also play a role into this transport behavior. So also I just change between two ion, TF6 and the TFSI. So first I start with like UV spectral electrochemistry. So I just take two examples to show what they're behaving. So first we come into mind actually the doping process, the de-doping process and the doping process. We need to separate them. The polymer itself is kind of self-dope. And so what I did, I de-dope it first and then dope it. What we can say first, the de-doping and the doping is not actually symmetrical. So like we have, for the, I just marked the 0.6 volt, the absorption at the 0.6 volt, we can say actually there's a difference between these two. And also for TBA, TFSI. And another striking difference, like at the same potential, we can say lithium TFSI has a higher de-doping level, but TBA TFSI has a lower de-doping level. And also, like when we de-dope the polymer, the neutral peak at 860 will increase, and also the small peak at 490. And the bipolar one peak will decrease. And when we dope the polymer, the bipolar and the bipolar peak will increase. And if we further reduce the polymer, the bipolar, even the polar one peak will decrease with the polar one peak increase. So that is the electronic band structure, how it looks like. I also compare the CV of this one. All this polymer require a break-in process. So we can say we just do the different CV. And until like a few cycles, the CV will stabilize, as shown here. And the almost a peak height will not change, both for lithium TFSI and TBA TFSI. And when we compare this CV, we can say for TBA TFSI, it has the highest oxidation potential and the lowest reduction potential, and then sodium and then lithium. When we compare their de-doping and doping level, so I just separate compare them. We can see for lithium TFSI, it has the highest de-doping level at the same potential, and for TBA TFSI has the lowest one. But in their doping process, it's reversed. It has a reverse sequence. So generally, a large, more polarizable chi-die requires more driving force for injection, but a larger force for ejection. So that's why for the de-doping process, the TBA TFSI requires a larger driving force for de-doping. So for different electrolytes, they have different doping or de-doping level. And also compare their switching kinetics. As long as we work in a safer potential range, their switching reversibility is quite good. Here's like a few examples of the switching, absorption switching value like for 3 electrolytes. And also I compare their kinetics. We can say like for the de-doping process, the TBA kind of has the slowest kinetics and the lithium has the fastest. But well, in their doping process, it's reversed. So TBA has a faster doping process and the lithium has slowest the doping kinetics. And I also want to mention this polymer, because it's prone to dope. So in most of cases, the doping kinetics is faster than the doping kinetics. So further, if we want to improve the device performance for switching, most of the case, we usually need to consider how to increase the switching speed of the de-doping process, not the doping. So here, okay, we understand, okay, cation plays an important role, but also anion also plays a role in the doping and the de-doping process. So that's why I compare TBA, TF6, and the TFSI. We can see like TFSI at any potential has a higher de-doping level than PF6, and reverse the like trend for reverse persistence effect for the doping process. The reason is that like for when we have like TBA cation, which is harder for ejection, now TXI can injection can facilitate the de-doping process. However, like in the doping process, strong ion pairing of TXI with TBA will retard the doping. Well, when we have a lithium, basically the difference is smaller. Even for the doping process, they are just overlap. When we have a lithium cation, which is easier for de-doping, then the contribution from TXI kind of ignorable. So it's kind of complex, like energy consideration of the polymer cation complex and the cation anion pairing with the solvation. We also compare their kinetics. We can see when we have TFSI, the doping kinetics, sorry, de-doping kinetics is strongly enhanced. A second approach is to use EQCMD. I think like many people familiar with this. We coat the polymer onto the sensor and we measure monitor the frequency change and the dissipation change during the process from the air to electrolyte, and then with electrochemistry. So I use the viscoelastic model to model this data, because like the Strawberry model for rigid polymer can underestimate the thickness of the mass change. One interesting behavior of this n-PBDF, so we synthesize it into polymer in DMSO solvent. So then we coating this onto a substrate, then vacuum dry it. Interesting behavior like is the swelling or the mass transport behavior strongly dependent on how dry or how rigid the polymer is. Like if I do not dry the polymer enough, it will show like a higher swelling behavior. And if I dry it, let's say completely, then it will have a smaller swelling behavior. So I compare the n-PBDF under lithium TFSI, sodium TFSI, and TBA TFSI into PC first, and then to the electrolyte, the three different electrodes. First thing we can say, like, for example, into the PC, they have basically similar swelling. But then we'll put it into electrolyte. The one with the lithium TFSI has smallest swelling, and the one with TBA TFSI has the largest swelling. We say understandable because TFSI is bulky and heavier. It enters the polymer and largely, expand the field. Another thing I want to mention is like, okay, even for the same electrolyte, a dry film and a light dry film, the swelling of in PC and in electrolyte are different. So it's strongly dependent on the dryness and rigidity of film. So why I want to mention this, because it also will influence the mass transport on the electrochemistry. So here is the thing, like when I do a long time of CV cycling, about like 7 or 8 hours, and there's different CV ranges. So this is like, for example, a typical CV I did for this film, and with different scan rate for many cycles, because I want to understand its stability. We can say like the dissipation and the frequency oscillate during all this cycling. One thing for the less dry and the rigid film, like we can say there's a baseline shift. It tells us, okay, the film is continuously losing mass. What's the reason? Because the film is not very rigid enough. So during electrochemical cycling, it keeps losing mass because of the reorganization of polymer and maybe the expelling of the residue, DMSO. But when we have like a very dry film and the rigid film, so we can say, okay, we will have stable cycle performance. So also the mass transport behavior can be different. And so I just zoom in, just take one a cycle at one scan rate and at one potential range. A good sign is like we can see the charge change. I mean, it doesn't matter if I did this one like several hours ago and several hours later, I pick the CV form like several hours before or several hours later. The charge change is basically the same. So I did many hours of cycling, but the charge capacity keeps stable, both in the less dry film and the dry film. But the mass transport can be different. Because when we have like a less dry film, by cycling, we make the film become more and more rigid. And we can have a smaller mass transport during CV than before. Well, when we have a very dry film, so the mass transport like several hours before and several hours later are the same. It's kind of interesting because like for many polymer, we worry about the like ion trapping. Like during like electrochemical cycling, we have like ion solvent accumulate into the polymer, and it will have caused some mechanical failure of the film. Otherwise, in the n-PBDF, what we can see is like we just see the polymer become more and more rigid. So we'll never see like a mechanical failure happen for this polymer. So it makes it like a good conductor, or like to replace ITO or to replace any other like organic conductor alternatives. Here's a little bit of information about like the mass transport. Maybe it's not the main focus of our project. I just want to mention it briefly. So I compare one cycle of their charge and the mass transport. Obviously, like the one with TBA has largest like mass transport than sodium and than lithium. And what is also interesting, like, is zoom in for the lithium TSI. During the de-doping process, actually, we can see a two-step mass change. So at first step, we can see, okay, mass decrease with increased potential. That makes sense because we have lithium ejection of the polymer. And then we have a small increase here. So even for the de-doping process, now we have a mass increase. So it's quite understandable because TSI also plays a role in. Now we can see the ion injection in the de-doping process of lithium TSI. I think now can provide us like the fingerprint of the ion participation. I mean, even in sodium and the TBA TSI, it also participated, but because the sodium and TBA has a large mass, so we cannot really see the TSI contribution from bare eye. There may be like a small two-step here, but we are not able to see. And also, if we have like a less dry film now, the mass transport is much heavier. I mean, but if we cycle it enough long, it will finally reach the same level of the dry film. And another effect is like for the ion. The ion, like I compare lithium TSI, lithium PF6, and lithium BR4. They have similar charge capacity, but they also have different mass transport. I mean, we can say, okay, lithium PF6 and lithium BR4 is heavier than lithium TSI, which is understandable because we assume, okay, TSI participate in the process, but the PF6 and BR4 may not. So TSI actually, its mass transport is like on the opposite direction of the chitin. So it will compensate the mass. So because of the compensation of mass, now we can see a small mass because we have TSI. But the difference between lithium PF6 and lithium BR4 is kind of interesting. If we assume they both do not participate into the doping and de-doping process, then the difference may come from the solvation of this two electrolyte. Because lithium form a strong ion pair with BR4, surrounded by PC solvent. So in order to break this ion pair, so we need like a larger solvation rate. So that may be the reason the BF4 had a larger mass transport than the lithium PF6. Then and also I compared TBA PF6 and TBA PFSI. The difference is that like TBA PF6 has a larger mass transport than TBA TFSI, which is also understandable because TFSI compensates the mass change, while TBA PF6 do not. So there will be a mass difference between these two, even though they are charged kind of the same. So the last part I want to mention briefly is the OECT. So even in OECT for this polymer, we need to consider their de-doping and the doping process separately because they are not symmetrical. So here's an example of their transfer curve. We can see for TBA-TSI, we need a higher gate voltage to de-dope the polymer. But for lithium, we just need a lower gate voltage. And one thing for TBA PF6, we cannot really de-dope it into a very high level. I didn't do that because the reason is I found that if I want to completely de-dope the polymer will degrade and show very decayed performance. But for other two electrolytes, it's okay. Then I also perform their output curve and then convert the output curve to the transconductance plot. We can see clear, this is for the de-doping process, this is for the doping process. So for the de-doping process, we can see lithium is either for de-doping, sodium is second, TBA is the third. And in the doping process, it's reversed. So there's a distinct VG shift among these three electrolytes. Well, when we change to lithium, the sodium and TBA TFSI, it's kind of different. When we say their transconductance plot, I mean, their separation, I mean, even though I tried many times and even make an arrow bar here, it's not as large as the PF6 plot. So why? Because in our like spectral EChem, there should be a large difference. But in OECT, the difference is not as large as before. So the reason is like in the OECT, we just have a drain voltage. So TFSI as organic ion, it's kind of easily diffused along the channel horizontally by the drain voltage. So it will compensate the Kaidan effect. So finally, it will just mitigate the difference between the three TFSI Kaidan. But when we compare like the one with the same Kaidan and different ion, so we can see the one with the TFSI shows like a easier or lower gate voltage for de-doping, but like a higher gate voltage for doping, and the separation between TBA, TSI, and PSA is even larger. I mean, there so here, so this is the categorization I have done so far. So generally, like in n-PBDF material, the larger, more polarizable Kaidan facilitate de-doping, but impede de-doping with smaller injection but larger ejection kinetic barrier. The anion transport is played as a secondary parallel process, where its contribution depends on the interplay of the Kaidan and ion. And the mass transport started by EQCM, both include the ion and the solvent transport depend on the electrolyte, but also depend on the rigidity or the dryness of the film. But well, the good thing is like, okay, the charge transport is barely affected by the electrochemical cycling. And in OECT, the performance can be a little different because there, I mean, the migration of the ion or Kaidan along the channel can also play a role. So, I mean, if we want to use this one as a conductor, polymer conductor to replace ITO, it has a very promising future because we didn't see any kind of like untrapping. And it shows very good stability and reversibility and the electrochemical cycle. So there are a few like ongoing study I'm going to carry on with this polymer. Like for example, study to decouple their mobility and volumetric capacities by different measurements. And also, for example, because we have different like doping de-doping behavior. We can study the polymer by microstructure characterization like GVEX or in situ AFM. And for now, I use PC. But in the future, I can use other solvent or like insolvent for if we want to like address the bioelectronics study. And there are a few synthetic design processes we can carry out like for this problem. So so this is my study of my of the n-PBDF material. So I'm happy to answer any question. Thank you.
Melissa?
Yes, Alyssa, have a question. Kidding. Hi, Songyan. Just
Hello.
one of the questions that I had is, if this is something that's going to be used as like an ITO replacement, have you thought about kind of like charge transfer kinetics of using this thing to actually drive like electron transfer reactions or anything, like getting some kind of kinetics parameter or characterizing it in that sense?
So you're talking about electronic transport from the conductor, the n-PBDF conductor, if we use to replace ITO to the heterojunction, or you're talking about from the electrode to the polymer to the conductor?
Just using it to I don't know, do something like just like a ferrocene type electron transfer reaction, or just some kind of like just some kind of like charge transfer reaction to see how it performs as a working electrode against something like a metal, or even just like other kinds of conductive polymers, or just ITO.
I mean, it can be. So because like for we have this basically the CV here, right? It's kind of like if we have a better energy alignment, we're able to just use this one to drive redox reaction, like what we did before P3T, right? So I think there's no problem. But if we want to use this one as a in the photoelectrochemical cell, because the polymer itself is doped, it's not like for a semiconductor, like I mean, if we want to have a light absorption, we create exciton. So I think in the beginning, this one should be not conductive in the ambient condition. But like for this one, it's not conductive at the beginning. So I don't know if we can use this one to build a heterojunction for photoelectrochemical cell study. So for now, I only consider as a conductor to replace ITO. We also actually we try to chemical dope the polymer by adding some oxidant, and we another one of my colleagues actually did this job, and we're able to like almost fully dedope the polymer by adding some oxidant. Then I think maybe we're able to make it as like a heterojunction in that case, I guess. Yeah.
Thank you.
Yeah.
No, actually, to answer this question simply, actually, in the previous slide, actually, Songyan did actually show actually using this conducting polymer as a conductor to drive the oxidation of the polymer.
Yes, we got like a electrochromics device here. We got like n-PBDF as a conduct layer. You can image to, I mean, also to adhere to another polymer. So when we do electrochemistry, the color of the polymer change, and it do show, like, I mean, good conductivity between the n-PBDF and the polymer, and the electrochromic polymer. So
yeah, simply actually you can do electron transfer to actually the solution or the same film on the top of it.
I've got some questions.
Hi, Dr. Armstrong. Yeah.
So I may have missed this. What solvent
PC.
do you dope this polymer in?
Dope the polymer. I mean, okay. Actually, In the synthetic approach, actually, we dope the polymer already. That is in DMSO.
All right. So then you put it into a solvent to study the de-doping process.
We put into a solvent to study the electrochemical doping and de-doping process.
Right.
That is polycarbonate.
Polycarbonate. Could you do the same thing in water?
Yes, actually, there are a few studies, maybe 2 studies talking about do this one in water. Yes, we can do a de-doping in sodium chloride.
Okay. All right.
Okay.
All right. And it's stable under those circumstances.
And it's not as stable as in a PC.
Got it. Okay.
Yeah, because the polymer is kind of hydrophobic. There's a problem between the ATO, a polymer between of the ATO and the PBDF, because it's hydrophobic, but if you have water accumulation, kind of delamination, if you de-dope it into a higher potential, but there's a safer potential range. But also there's if like oxidized to 0.9 volts, then it will be in danger.
So when you make this polymer and you put it on whatever electrode to study the doping process, it starts out as a doped polymer.
Yes, that is a doped polymer.
And what is the counter ion that's in the doped polymer? Is it lithium?
Proton. At the beginning, it's proton.
It's what?
Proton.
Okay, protons. That's right.
Proton.
All right. So when you do the de-doping, do you think you're expelling protons or taking up anions?
Yes, it had ion exchange effect. So I didn't mention this one because it can be seen from like a swelling process.
Yeah.
I mean, take iron like electrolyte, it's passive swelling. When we dip in PC, it swell first. Then we have like an electrolyte. So there also volume increase. The volume actually calculated from mass increase. So if there's a mass increase, that definitely means, okay, we have other cation, a larger mass cation come into the polymer to replace the proton, because their conductivity kind of keeps relatively stable.
Yep.
So there's a huge like ion chain effect.
Okay. So the as deposited polymer is conducting.
It's conducting.
So you probably then could envision building an OPV on top of this thin film and just make use of it as the back contact in an OPV.
Yes.
Have you tried that?
Oh,
we did that. We actually we are not using OPV. We use a perovskite. Actually, use it for as a conductor, a transparent conductor for perovskite. It works just as ITO. Yeah.
So is it charge selective? So in other words, is it a good hole transport or electron transport, or is it just like ITO?
So at this point that we have actually not optimized the device and the interface. So actually the field factor actually relatively low, even though the efficiency can approach to 12 to 15% out of perovskite. But the field factor actually right now is only about 60%. So there's something going on at the interface when actually it is used as a conductor.
Well, it's an interesting, I mean, it'll be a source of protons potentially for the A-side cations in the perovskite. That may or may not be a good thing. It'll certainly keep those protonated, which is something that you absolutely want to do. I'm really interested to see whether you could put a blended heterojunction OPV on top of this thing and what the performance would look like. If you really want to replace ITO, that's one of the ways to do it. Or build an OLED on top of it.
Yeah. I mean, since we are able to use it actually for electrochromic device, I think actually for the solid state device where ion transport is absent, the probably would be actually even more favored than actually electrochromic device.
Right. Right. Yeah, I think it's potentially pretty interesting in that regard. Is it truly transparent in the visible though, because of the polaron absorption?
So
I can say it's transmissible.
So the transparency actually is thickness dependent, obviously, and for it being actually a conductor, if you actually using somewhere about 40 nanometer, you would actually have transparency around actually 80%.
Okay.
Yeah. In a visible range.
All right. Interesting.
Obadiah, did you have a question?
I did. Neil actually asked the first part of it, which was, what's the counter ion? And are you expelling it, or are you bringing, essentially exchanging it? But I did want to follow up on that a little bit. And then I find it interesting that you do have some trends in the d-doping depending on the cation. But if you're starting out with protons in there, I would, and one possible mechanism is like you would think that when you d-dope it, you're either expelling the cations that you have, or you're intercalating new anions to help compensate them.
Right.
And so I would sort of expect the correlation to be with changing the anion, not the cation in the solution. And so I guess I was wondering a little bit if maybe it had more to do with exchanging a proton for the cation in the TFSI, and essentially the relative acidity of those different sort of conjugate bases that you've got.
Yes, actually, this is one of the questions we have been trying to figure out. Actually, whether the pH will increase in the solution or not, and considering actually the relatively thin thickness of the polymer, and that the amount of actually a proton even it is coming out, it doesn't significantly make a pH change. Yeah. We try to measure the pH change, and it's not very obvious.
Okay.
Either it does not come out, or actually come out not in enough amount, and which we can calculate, of course. Yeah.
Yeah, it'd be interesting to see the kind of the opposite experiment where you change out the anion instead of the cation as well.
Yeah.
Oh, I think I did change the anion, like PF6 and TFSI.
Right.
Yeah.
Oh yeah, you do have that.
Yeah, I do have that.
Oh, the PF6 versus the TFSI, right?
Yeah. So that's why there's a difference between PF6 and TFSI. So that's why I conclude, but the effect is not large enough. So that's why I conclude that TFSI injection for d-doping is kind of like a parallel secondary process, in addition to the cation ejection, which can be also supported by the EQCM, because the mass change trend of these two are the same, but the absolute value is different, because TFSI actually has the opposite mass change like behavior than the cation. So when we have like PF6, for example, this one, we compare TBA-PF6 and TBA-PSI. This is PF6. So the mass change, the measured mass change is larger than TFSI. The reason is that TFSI here actually, or TFSI here, is actually because it has some like reverse mass change from TFSI. So that's why they got difference in mass.
Okay, it's going to take me a little while to digest these figures.
Yes, this mass change is kind of convoluted together. It's a two-step process.
I just want to mention actually that Enroute does have a polymer in hand for a few months now, so you may like to play with it if you want to.
Yeah. Yep.
What's the
And yet-
substrate you typically put this polymer on? Do you just put
It's
it on ITO or whatever?
ITO. But for EQCM status gold, that I cannot change.
Mm-hmm.
Yeah.
So we have actually put the polymer through spray coating on glass and PET, and as a purpose to make actually transparent conductor. And then this conductor has been used for perovskite solar cells and has been used for actually dual heating purpose.
Got it. Okay. Really interesting stuff. I'm going to have to run. I'll talk to you guys soon.
Yeah.
Any other questions?
Just one. Hi, thanks for the talk. It's very interesting. As a non-electrochemist, when you have all these graphs, or you're measuring the mass as you change the voltage, how do you physically do that? Do you just like take it out of the EChem cell and put on a balance, or?
Oh, okay. That's how EQCMD works. It's more about physics. Like we put like we got a sensor which is designed specifically for the instrument. So either a bare sensor or we coat the film. Then we put it into the instrument, and because it has a ozone underneath, so it will oscillate the sensor at a different frequency.
Oh, I see. Okay.
So then you have different harmonic frequency. Yeah, we can measure the harmonic frequency change and convert it into a mass change. So yeah, the basic information.
Yeah. Cool. Thank you.
Thank you, Songyan. I have some questions.
Mm-hmm.
First is, did you use polycarbonate as a solvent?
Mm-hmm. Polycarbonate.
All experiments?
Yes.
Because I just wondered, lithium ions have larger hydrodynamic radius than sodium ions.
Yes.
Yeah, but you mentioned the larger the ion size was, ion size affected the results, but the sequence was very different in active electrolyte. But I'm not sure lithium ion is larger in polycarbonate.
Yes, I think about that at the beginning. If we look at the doping and de-doping kinetics
as well,
it's kind of the same for lithium and sodium. Yeah, we think like lithium, because it's smaller and has higher charge density, it should have a higher solvation layer, right? I think that is what you mentioned. Actually, I tried to calculate the solvation number from the EQCM D, but there's one problem of me. I cannot really get an actual number of solvation number, because I convert the charge. If I assume like one charge equal to one Kaidan, then I can know the theoretical mass change from the Kaidan transport. So there's one mass, and I can also measure the overall mass change. In practical, usually that mass is larger than the theoretical mass. So then I can consider the difference. The difference is the solvation number. You can say from my calculation, that is the solvation number of lithium TSI is smaller than sodium TSI. Yeah. But this number is not accurate, because one problem is because I also have TSI transport. Because the mass of lithium is so small, then the mass transfer of sodium TSI compensates more into this condition, and then make my calculation not correct. because I cannot make, I mean, in this TFSI condition, I cannot say, okay, only Kaidan participate in transport. Even say, I mean, I can assume that, but I mean, in reality, it's not. So it's hard for me to tell actually the solvation number difference between the lithium and sodium. I know the TBA will have higher solvation number, but lithium and sodium is hard to tell right now. I mean, I will study further, like just exclude the effect of DSI and see whether lithium has a larger solvation or not. But it's not actually important in determining the device performance because in these two Kaidan, they're almost the same.
Okay, and the second is I had a plan to use PB. Sorry, I forgot the
n-PBDF. Yeah, n-PBDF.
n-PBDF. Yeah, to use to replace ITO because when I use PSS as a whole transport layer, I observed the delamination when I applied more negative potentials.
Negative potential. Okay.
Yeah, because PSS was reduced and swelled and delaminated by reduction potential.
In water?
The PSS was swelled and delaminated by de-doping.
Yeah,
under reduction potentials.
Yes.
What is the potential you're using? How negative you want to go?
Sorry?
How negative?
How negative?
I applied 0 with light, 0 volts with light exposure.
Oh, 0, okay.
Yeah.
No, that's not a problem for n-PBDF. n-PBDF could be as stable as actually minus 0.5 to 0.8 volt without actually further irreversible reaction. So in this range, actually is very safe.
Yeah, then that will be good for cathodes. And I wonder one more thing. Have you ever thought about tuning energy levels of a PBDF?
That would be very difficult because this polymer is designed to be simple and if you look at the structure, there's not much actually that you can do with the structure. There's just no functionalization site available. The only thing actually you would be able to put actually is on a benzene ring, then you just destroy everything in the packing. So if you put actually a substitution there, so it's almost actually that by luck actually is everything is optimized for its conductivity. Yeah.
Okay, thank you.
We could we could actually change actually its energy level relatively straightforward, but then you will not be conductive as it is. Yeah.
All right. Are there any other questions? I'm not seeing any hands. Well, and I think we're just about out of time. So thank you again, Songyan, for the presentation. Those of you, as a reminder, this was recorded, and so it will be on the Specs website if you'd like to reach out or watch it again. And then I think too, from what I've heard from the questions, Songyan, it might be helpful for you to tell or send us an email, or if you want to send it to me and I can send it out to the center on how to process your polymer. So if we all have it in our glove boxes, I think we just need the recipe on how to make the films.
So it's now in DMSO based.
Okay.
Okay. Yeah, I will tell you. Yes.
Okay.
It's kind of tricky, like when you want to put it on different substrates.
Okay, I think that would be good if you've got tips and tricks that you'd be willing to share. I think the number of people on the call would really appreciate it.
And also, it also depends on your purpose. And if you're looking for high conductivity, then you have to be processed from DMSO. However, that if actually the conductivity is not your major concern, we do have formulation from alcohol-based ink, which could be then spray coated, actually inkjet printed, whatever the way you want it to be. So it really depends on what you want to do with it, and there are different solutions for the problems. Yeah.
All right.
Yeah, just send an email if you want to know how to do that.
Okay. Sounds good. Thank you, everybody. Have a great day.